the wildest thing on this campus is if you head down the hall going that way towards the drinking fountain in the restrooms, there's an electrical room in there. That one, if it's ever open, is like 90 decibels loud. It's horrendous.
About a kid that like snuck in on the college campus into a utility room.
Oh.
Generator.
Yeah,
That's not part of the game.
that's terrible. Oof.
Great story.
Well, let's start calculus on that note. Welcome back, everyone. We're talking about people getting vaporized in electrical closets, but on a more serious note, we're on example 5 at the moment. And I'm not going to try to rush to or complete these notes today. So if we take extra time on Monday to finish it off, we'll move the due date as normal. Well, any questions at all, folks? I don't have a whole lot of announcements for us today. Okay, well, let's get back to where we left off. We ended class last time looking into centers of mass, but we were only looking at the one-dimensional case. So this was kind of a fun problem. I think they're all really fun, actually, because these are problems where humans have kind of an uncanny intuition about this. Visually, people are surprisingly good at spotting the center of mass. And we did this as an experiment in class. Everyone said to stop the red dot here. And it turned out we were all highly accurate, off by just maybe about a half a value there. So the write-up of this was, to get the center of mass, you first have to form this product, the mass times the coordinate. Let's do the full summation. And what you're calculating here is m. That's this value m that went here and here in the numerator. It's called the moment of the system about the origin. I don't feel like I explained that too well last class, so let me try to give a little bit more background when we're saying about the origin. Well, this is the origin right here. Let's go with purple. And the fact that we got a positive quantity on here means if there's no fulcrum whatsoever, or rather, if the fulcrum is right on the origin, that means this thing is going to tip going that way. We got a negative value instead, it would have tipped going that way, rather. So that's what we are meaning when we say the moment of the system about the origin, the tendency for the system to become unstable and move over. But once we calculate the actual value here, x bar, the moment, it means we put the fulcrum right here at that location, and the whole system will balance. So to make that happen, the next thing we formed was this equation. But that's not too bad. That's just the total mass of the system. We divided here, and we got the actual center of mass, 2.65. So our goal next is we're going to expand on this and do it in 2 dimensions. Any questions first before we take a look? Okay, so going off to the next page, notice we haven't done any calculus on this topic just yet, but we're getting there. So from 1-dimensional to 2-dimensional, here's what the situation looks like. Instead of having the moment about the origin, we now have my. My measures the tendency of the system to rotate about the y-axis. We'll also calculate mx, and that's going to be the tendency to rotate about the x-axis. So far, so good, but watch out for this right here. This gets me every time I look at these notes. We call it my because it's the tendency to rotate about the y-axis. But the actual equation is taking the point masses and multiplying by the x coordinates. So there's kind of a misdirection when you read this, but the more you visualize it, you'll start to see, well, it makes sense. It's just confusing at first. Let's try to make it to make sense. So here's a set of axes to start off. What we're dealing with is another rigid system where all the mass is located at points. Here are the masses, and those are the points. So let's just draw out something generic. Let's say we have a point here with mass m1, point here with mass m2, point here with mass m3. We're imagining this is a rigid system connected by maybe a plate of negligible mass. And so we're thinking that at these point masses, these are so massive that for this whole total system, it's as if all that matters are those three locations. So that's how we're imagining this, negligible mass on a rigid system. So when we go to calculate my, we form this, and when we go to calculate x bar, we do as we did before. We just divide by the total mass m. So when we say my is the tendency of the system to rotate about the y-axis, here's what we're imagining. Take off the x-axis just temporarily. If my is positive, that means this whole thing is going to tip over going that direction, falling off the y-axis going that way. If my is negative, that means this whole plate connected by the three line segments is more likely to tip over going that direction, falling off the y-axis. Does that make sense to folks so far? Okay, let's do it again just for completeness with the, whoa, didn't mean to scroll, other axis. So what's going on with mx? Notice it's mx, but you take the masses times all the second coordinates, yi. So what mx measures is the tendency to rotate about the x-axis. That means we're visualizing this with no y-axis at all. The same issue as before. If this thing comes out as, hang on, let me double check this. Tendency to rotate about the x-axis, yes. So it should have been that way, there we go. If this thing comes out positive, kind of lost my way on there. Positive means the whole thing is not going to balance on the x-axis at all. It only would have to be 0 to make this balance. So positive quantity means that whole plate falls over onto the ground going this way, off of the x-axis. So it'd be kind of like this, flipping up and over. If instead we had negative, then the whole plate would fall off the x-axis going that way, falling to the ground. So that's the way we visualize those different moments. But the nice thing is, once we explored how to do this in 1 dimensions, we're not really doing anything entirely new. Once again, take a look at the formulas. We take the moment about the y-axis, divide by the total mass. That's going to give us our first coordinate, x bar. Second coordinate, y bar, is going to be the moment of the, let me say, the moment of the x-axis, mx, divide by total mass. So what we're producing here is a pair of coordinates, x bar, y bar, which is going to be the center of mass. So center of mass means we're trying to find a coordinate x bar. X bar is going to be just some value, say, going this way along the x-axis. Find another coordinate y bar. It could give us another line going this way across the y-axis. And where they meet right here, that's the center of mass, x bar, y bar. The way we visualize this is that solid point for x bar, y bar is where you would put a pinpoint under this system, weird looking triangle, to make the whole thing balance. So that's our way to visualize. Any questions at all, folks, with that so far? Okay. And the fact that I'm claiming center masses right here on this problem means masses M1 is probably the most massive thing in the whole system. M2, maybe a little bit more massive. And M3 probably has the least amount of mass, but it has a whole lot of leverage to cause it to all balance right here in the end. Doesn't matter how many points we put in, we're really just using that. The law of the lever is what gets us all these results. Kind of curious in a way. We didn't really prove the law of the lever for multiple points, but we showed how it could be done with a 2-point situation. So that's what the setup looks like. Let's give this a try for another problem down below. These are real homework questions, and they could potentially be short exam questions. I'm not saying necessarily example 4, example 5 is on the exam, but if the exam is the right length where a short question can be fitted in, it could be one of these. So these are not just one-off kind of questions. They can potentially come back, in other words. Let's give this a try from scratch. It says masses M1 through M4 are located at points P1 through P4. Find the moments MX, MY. When you're doing this as a homework problem or as an exam problem, you don't really need any kind of illustration. But This is our first time doing it, so let's actually draw this all out, just to show about what's happening with the process. First thing I'll put down are these ordered pairs, so -4, 2. Here's our first point, and at that point, we have mass M1 for 5. Then next point is at 0, 5, 3, 4, 5. On this axis, we have mass 2. Could say 4 kilograms if we want a different definite unit on there. I'll just draw the masses here so we don't have too much information. Then P3 is at 3, 2. 1, 2, 3, height of 2. And there we have a mass of 3. And last one, at coordinates 1, -2. So we're here. We have a mass of 6. Then once again, imagine that there's a rigid system here connected at those point masses. Maybe some kind of basic wireframe or something like that. Maybe it's wood. So our goal now is to find out where this is going to balance. Looking at this, I think it's a little bit harder to predict maybe versus what we did on the last problem when it was just the y-axis and point masses. But if we still had to predict, any volunteers for right about where the dot should be, center of mass? Should it be somewhere on the left, the right, for example?
You with -1, +1.
Right about here. I think that's a pretty good guess. So let's say right here temporarily. Looks like about here for center of mass. So the mass is most massive here at 6. So I agree the point should be pretty low due to that. And we have a lot of mass going this way. So that looks pretty good to me. Any other guesses on this one? Okay, that's, I'd say, a pretty good thing to do when you're working these problems. Get some intuition by just guessing about where it should be. And if we are in the right ballpark, then that's excellent. If it's somewhere off, who knows, that maybe we're just a little bit off in our thinking about it, and that could be pretty informative too. Well, the thing we have to do next is, let's start calculating the formulas we need. We need total mass M. That one's pretty quick to calculate. You just take the mass as 5 plus 4 plus 3 plus 6. So the total mass of the system is 18. Next computation is a little bit longer, but not too bad. Let's calculate the moment of the system about the y-axis. Now, again, the format here is tricky. If it's my, the formula goes like this. Summation as I goes from 1 to n. This is the generic formula. N would be a 4 in this problem, but as a generic formula, it's mass I times xi. I always hate those conflicts of directionality, but if you see a y variable here for my, you're using the x coordinate, kind of a mismatch in our brain. But that's not too bad of a product and a sum. We'll take these masses up here, 5, multiplied by the first coordinate, -4 for the first one, and just go down in that pattern. Next mass 4, multiplying by the second coordinate here, 0, plus a mass of 3, multiplied by the third x coordinate, which is 3 as well. And finally, add to it the final mass of 6, which multiplies the last first coordinate, 1. So that's now just a little bit of arithmetic. We've got -20 plus 0 plus 9 plus 6. So that's going to be 15 minus 20 for a value of -5 altogether. Does that look right to folks on that first product? Okay, so now that we have that, we can go and calculate x bar right here if we'd like. Let's go and write out that x bar is going to be the moment about the y-axis, divide by the total mass. So we'll take -5, divide by total mass M, which is 18. And I forget, I do need a calculator here. Let's open up Desmos. I don't usually use a calculator in this class, so I always seem to forget when I do need one. It gives us a good reminder as well. Don't forget, calculators are allowed on exam too, so good to have your designated calculator that you're always doing with homework always around so that you don't make a weird sudden change on an exam day. So -5/18 gives us a -2.77. Let's say -0.28, rounding to 2 decimal places. So you know what? That was about right. This should have been on the negative end. Our point just needed to move a little bit more off to about here. But it was about right. I don't know for the height, but I think we're getting pretty close to there. But this is what we've determined. If you take that value and put a line that goes like this system connected between the point masses will balance on that vertical line. We now need to come up with the horizontal line and intersect to get center of mass. But any questions at the moment, folks? Okay, let's try it all over again. We need the moment about the y-axis, written as mx. Let me see if I can get some extra space here. There we go. But essentially, you're just doing this once again, but you're multiplying by second coordinates. So this will turn into mass 5 multiplies that second coordinate, 2, plus down the line, mass 4, multiplying by the new second coordinate, 5 on that one. The red dot is like my finger. I sometimes have the wrong numbers unless I'm really pointing at it. Then plus 3 multiplied by the third second coordinate. That one's a 2. And last, plus a point mass of 6, multiplying the final second coordinate, which is -2. So a little bit more arithmetic. This one comes out as a 10 plus 20 plus 6 minus 12. So altogether, that's 36 minus 12. Looks like a 26 altogether. That look right to folks so far? 24. Thanks, folks. Arithmetic is a bad spot to get this one wrong at. 24 altogether. Appreciate it. So now next, we got our y bar value from doing all that. Y bar is the moment of the system about the y-axis. Divide by your total mass. So that one came out as a 24 with the correction. Divided by total mass of 18, that we calculated at the first step. We have a coordinate. It's not in reduced form, but let's go for decimals. It is an applied problem, so I'd say that's appropriate. You are welcome to do the same on all of section 8.3. I just say round to what makes reasonable sense. 0.4 divided by 18 to 2 decimal places again. This is a 1.33. Or you might say 1.3 bar for repeating. So if it's there, this red dot just needs to move about right here. So the initial guess given by Bryson was about right here. And you know what? That's about right. I barely budged the point at all when we calculated it exactly. So that location is the center of mass. It's at approximately -0.28, 1.33 for center of mass. Well, we did it, folks. That's what this looks like in the 2-dimensional case. Any questions at the moment? Okay, so again, we didn't use any calculus whatsoever, but this is where the reading in the section 8.3 is actually quite good. I complained a lot at the start of these notes. If you're doing this kind of stuff, I'd say don't get too discouraged with the reading in that section. It starts off nice. He does a great discussion on the units. Then it kind of goes haywire. The author attacks all the problems in this way, a Riemann sum every single time. And I think, again, it takes a really well-prepared student to take that information and actually answer the homework exercises efficiently. So the reading starts off bad. I would once again encourage you to use this formula for all problems, just to make it more approachable. But once you get down to section 8.3, The author must just like this problem better. I'm not too sure. It must be center of mass is his favorite. His discussion on this portion right here is really rather good. He gives a nice, clear derivation, provides the actual formulas, so you're not using Riemann sums each and every time, and those are the formulas. I put here some information on how you would do the derivation, but we'll skip this one. The reading on that is really pretty good. Even if you're just skimming through the reading, you can get a really good idea of how it goes. So just for a sketch of what the derivation is, we're going to take a region R that goes like this. Let's say there's a function here because we want to deal with a nice continuous function. So it could be something that goes up like that. There could be two functions. We'll see that on the very bottom of the notes when that formula comes up. Let's imagine this is our situation. There's one function, y equals f of x. We also have one other function. We have a bound down here. This is y equals 0. We have another bound right here. That would be x equals, let's give that a definite value, sort of a. That gives us a vertical line segment. We'll only apply this much to cut off the area here instead of the total vertical line segment. Next one will be x equals b. And what we get is a bounded region in the plane. So that's our region R. So we have a plate called a lamina with uniform density this time. So instead of having point masses at various locations, we're going to say that the density is now uniform throughout this whole plate. Imagine it's maybe something like this, for example. Uniform mass across occupies a region R, so there's our region. We wish to locate the center of mass of this plate. Again, visually, we were probably pretty good at this. It's possibly somewhere in the middle. It might budge to the right because of more mass over here. And maybe right around there could be the center of mass. Our author does a really great job of just taking point masses and showing what the derivation looks like with Riemann sums. But here's the punchline down below. We've done a lot of derivations, so I thought we'd skip this one this time. To get x bar, we take the reciprocal of the area, integrate from a to b of x times f of x. And for folks who have taken Math 3352 probability, you might recognize that formula. That's the formula for the mean when you're dealing with a continuous distribution. This one is its own thing, though. If you want the second coordinate, the derivation gives you a wilder looking formula. I can't think of anything too familiar in probability theory where this one comes from. Still involves a reciprocal of the area, but then we take a half times the function squared. And that would be what's generating the function. So that's how all these problems kind of go. Any questions, folks, about the quick sketch up here or the formulas below? Okay, well, let's try it ourselves. If this was a real exam question, I think I would give you the plot for these kinds of things. That way, as you do the problem, you can judge even in the exam setting if you're on the right track. You're basically doing what we did above here, guessing the centroid before you even calculate it. Again, humans are remarkably good at doing that kind of stuff. And so here's how it's going to go. We have 4 different curves. 3 of them are straight line segments, and this is the one you usually think of as a curve, e to the x. We want to plot this all. We could do this by hand, but let's make Desmos work for us and get a nice plot. Let's go y equals e to the power x. For x equals 0, x equals 1, think of that as being a domain. So go curly brace, 0 less or equals x, less or equals to 1. And this is our region right here. I can get a good zoom on that. That should do the job. So on a real exam, you'll have something like this to work with. I might not use Desmos, I might use a different computer software, but same kind of idea. You'll have a graph of the function. So there's y equals e to the x on the very top here. What you would have to do if you choose to on your graph is add the extra information. Let's start with x equals 0. That would be this vertical line segment. only putting in as much of that vertical line as is pertinent to the problem. Here's x equals 1. That's going here all the way up. Again, this is stuff that wouldn't be on the exam question. You would draw this up if you choose to on an exam setting. And for y equals 0, that's just giving a bottom so that you actually really have a bounded region. So this is our lamina. Imagine it's just some weird piece of metal, maybe some cast off, something like that. Or maybe you're building something, piece of a fender, who knows? It's going to have a uniform thickness, uniform density. And we want to know, where's the center of mass? Well, eyeballing it, would you agree that it's not necessarily for the x coordinate right about here? Would it budge left or right?
Right.
Yeah, because of this extra mass right here, it's got to move a little bit more to the right. Then if we're here, I'm halfway between 0 and 2. Should it go up or down from that location?
Slightly.
Slightly up? I agree again. Well, I don't know. That's kind of hard for me to actually visualize. Let me put down a couple marks here. Here's the halfway mark. Now, is the area above or the area below bigger?
Below.
Sorry, say again. Well, this would be at 1 right here. So yeah, I think it might be below is a little bit more area. But it's kind of hard to my eye to actually see it. So I'm really not sure on this one. If I had to guess, maybe there. But I'll leave it up to the class. Should we budge that from any direction on there, up or down, left or right?
I would be up to that how much longer it is.
A good point. That does produce leverage on this, so that might actually drag it upwards.
Also really skinny, so it might just be right in the middle where you have the line drawing.
Like right over here, rather? You're saying here?
Yeah.
Probably. This one's kind of tricky to me. I think it's that sharp shape that's kind of throwing me off. But what we do have going for us, and I'm going to try to do on a real exam, is the scale is 1-to-1. I don't have anything weird going on where it's like, say, a compressed axis and elongated in the vertical direction. I'll try to give you a 1-to-1 scale so you can make a reasonable guess, like what we have here. You do not. It's only if you get a weird answer on the exam, if you eyeballed it and thought, hey, that doesn't make sense, you would know maybe there's something with haywire at some spot. But no, it's not required to make a guess. I think, now that you mentioned that, the actual homework questions do say to make a guess, but I'm not too worried about that. Once you do the computation, it's like your guess didn't matter, right? But I think that they're trying to do the same thing. It's trying just to get you to decide if your answer is reasonable. Well, I think we're ready to start. There is a sequence of steps for this. Step 1 is calculate A. A is the area of this region, the lamina. And that's not so bad. This is just a definite integral. We integrate along the x-axis from 0 to 2. To get the area, well, we just find the area under that curve, e to the x, dx. So that's kind of a relaxing computation. This is the world's best antiderivative ever, right? Antiderivative of e to the x is itself.
Can it be 0 to 1?
Oh, thank you for spotting that. I said 0 to 2. I'm not sure where I got that. It ends right at 1. That would have helped me out, putting a 1 on the actual scale. So we'll go from 0 to 1. Thanks again for catching that correction there. And that means we're evaluating this from 0 to 1. That gives us e power 1 minus e power 0. So this is just e minus 1, the total area of that region. Any questions to that stage? Okay, well, it's not really a big deal to put down the steps. The major thing I want to communicate is that should be your first step for sure. Because either thing you calculate, the x-coordinate or the y-coordinate, you require that area. So to fill this out, I'd usually do the x-coordinate first, but it's totally up to you. Step 2, compute the first coordinate of the centroid. And by the way, if we say center of mass or centroid, that's always considered synonymous. I think you usually say centroid if this is the situation, plate with uniform mass. So that computation, again, this is kind of inherited from statistics, at least that part right there. It's kind of interesting. So you get X bar is the reciprocal of area. So 1 over E minus 1. So that part there gets thrown into that location. Then we're integrating from 0 to 1, not 0 to 2. We're stopping right here. We take X times f of X. F of X is the curve right here. We wrote it as y equals e to the x. Our functions, or formulas rather, always emphasize function notation. So this turns into 1 over e minus 1. Integrate from 0 to 1, x times e to the x, dx. So that's our integration to solve. It's not so bad. We need integration by parts to get through this one, but it's a fast integration by parts. Set up with u equals x. dv is e to the x dx. We chose u to be x because when we differentiate this one, it gets reduced in complexity. We get the differential dx equals 1 dx. Or let me try again. The differential is du, rather, for the left-hand side, equals 1 times dx. Or just du equals dx if you prefer. On this one, we're finding the antiderivative. We've done that once, and here it is a second time. Antiderivative of e to the x is itself e to the x. So that chart right here gives us this result. First, the reciprocal of the area. Then it's x times e to the x, u times v. That's evaluated from 0 to 1. Minus an integral from 0 to 1 of v times du. That's just e to the x dx. So we're integrating e to the x for the third time now on these notes. And now it's just a matter of running through the numbers. So let's see what we get here. 1 over e minus 1. On that first evaluation, we get 1 times e power 1 minus 0, putting in the lower limit. It's really 0 times e power 0, but it's all dead with a 0, so I'll just throw it at 0 there. Next, we have a minus from that minus. Antiderivative of e to the x is once again itself, and this is evaluated from 0 to 1. Does that look all right to folks so far? Okay, let's keep cranking it through. 1 over e minus 1 multiplies, from here we just have e, minus, I need another parenthesis on this one. I probably should have kept my bracket for clarity. There's the bracket coming back in. So for this negative sign, I put a parenthesis out front so I don't have weird double negative issues. We go e to the power 1 minus e power 0. In fact, we've done that once already, so let's just put that in. E minus 1. Next, we'll distribute the negative sign through, and we just about have an answer. 1 over e minus 1, this is going to be e minus e plus 1. So in the end of the day, this is just 1 times the reciprocal of e minus 1. 1 over e minus 1. That's a totally fine answer. If you want to give exact results on this assignment, I'd say that's pretty reasonable. We've been doing that for many assignments. But this is a one context. I think I would encourage you, throw it in a calculator. That way, if I get that this is the number 3, we're way off, right? The answer for the x-coordinate has to be between 0 and 1, excluding those boundary points. So this is a sanity check, really, at this stage. Let's put in 1 over e minus 1. And rounding this to 2 decimal places, it's a 0.58. Close to a 0.6. So that tells us, well, right here is at 0.5. We do have the x-coordinate in the right spot. It budged off a little bit to the right from 0.5. Well, that was so fun. We'll do it all over again using this formula up here. Any questions so far? Okay, let's use the method of saying this continues on to the next page. And here's our step 3. compute y bar. So we have to scroll down, but let's just restate the formula right here. For the center of mass, the y-coordinate, we take the reciprocal of the area again, like before. We integrate along the x-axis from 0 to 1. And then inside the integrand, they put the factor 1/2. The reason that factor 1/2 is not outside is it's part of the derivation, reminding you how it all went. In the derivation, a 1/2 comes out. And it multiplies the function to the power of 2. So that's our total setup from that formula. We just need to plug in the information. So reciprocal of the area was e minus 1. That goes into that location. The function, like before, is f of x, which is e to the x. So that's going to go inside there, raised to power 2. So here it goes, 1 over e minus 1. That's our first substitution. Limits of integration are already in at 0 to 1. There's 1/2 times. We're taking e to the x squared, so that's going to turn into e to the power 2x. Just for a little bit of an exponent discussion, if you take e to the x squared, that's what it looks like. And in that configuration, your exponents multiply together. So it turns into e to the 2x for that one. So we need to integrate this one, and it's a faster integration this time. We don't need parts on this. Well, after filling all that in, it's really just a matter of how you want to evaluate this thing. Let's write this out as 1 over 2 times e minus 1. For me personally, I try to get extraneous constants outside the integral. So I just multiply the denominator by 2, leaving it in the factored form. Integrate from 0 to 1, e to the 2x dx. Because the numerator, the power position here is a linear function, this is a good one to once again skip the u substitution. No harm if you decide to do it, but it's really rapid without. So without a u substitution, this is what we would get. 1 over 2 times e minus 1 multiplied by, give it a little bit of space, and put in antiderivative of e to the power of 2x. It's e to the power of 2x to start. And anyone spot the constant right in front? Good call. If this is a 2x here, you just put in a 1/2. And the reason for that is if you differentiate this, it's the chain rule. Derivative of e to the 2x is itself, so it'll produce that. But then you multiply by the derivative of 2x, which is a 2. It'll eliminate the 1/2. And so you produce only that by putting that factor of 1/2 in front. Again, u substitution works, but these kinds of problems come up so often, I would encourage you to analyze it in this kind of way, just to save a whole lot of time. Well, it's this part right here, e to the power 2x. We're evaluating from 0 to 1. So it looks like we need a new line, and now we're just really cranking things out once again. Hide example 7 down there first. So this could turn into 1 over, first let me fix my spacing. 1 over 4 times e minus 1. So I've combined the constant of a 1/2 here with that 2. Now let's focus on that parenthesis. We have e squared when we plug in 1, e to the power of 0 when we plug in 0. So this is 4e minus 1 down below, e squared minus 1 above. So I took this, just multiplied it into the numerator. That answer is totally fine, but in the back of the book, they probably wouldn't give that answer. Usually the back of the book, it's almost like they're showing off. They start to simplify things. This one does simplify. It's good practice with factoring. E squared minus 1 is a difference of squares. So it can be factored as e plus 1, e minus 1. Below is 4 times e minus 1. Gives that as a simplification. So now we've got e plus 1 over 4. And we're ready to approximate. So we're going to answer the question from above. Did that budge upwards or downwards? Honestly, I had a hard time really seeing that. It looked like that was a pretty good position. So the calculator, let's take a look. So we're putting that in, e plus 1 divided by 4 gives us 0.93. So the folks who are saying it should be below, good call, you're absolutely right. It was close though, off by about 700ths. So 0.93. Well, this would be a cool or a total answer right here where we have it, but it's not a bad idea to put in a big summary. We'll say triple triangle, or the triple dots for a triangle for therefore. Center of mass, which we can just use the symbol x bar, y bar, is approximately located at 0.58, comma, 0.93. So back up here on the display, let's correct that and just budget ever so slightly down. I think that looks about right. That is our center of mass. Well, how do folks feel about that one? Does it make sense on running through this problem? I hear you. Sometimes the algebra gets kind of hairy on these kinds of things. And so standard offer, some people are taking me up on this, so I appreciate when you write or drop in on office hours. If this is your work, but your coordinates are way off, just send me a file, a picture, a screenshot, anything like that over email. I'll be happy to discuss it. Or another option, feel free to drop into my office hours. It's always through this Zoom link. And the hours have Monday, Wednesday, Thursday, 3:30 to 4:30. So that's exclusively on Zoom. That's going to help out the people in the online section the most. And for in-person tutoring, I have these times as well. I kind of misspoke when I said this is for people in Zoom. This is really for anybody. If you're in the online section, you can come to any office hours. If you're in the in-person section, you can come to any of the office hours as well. But I made these specifically thinking there's an online section that couldn't come to the in-person one as well.
Honestly, it's not that difficult each step, there's a lot of steps.
That's the trouble. Yeah, I hear you.
It's that integral is that easy on the test. That difficult.
Yeah. What would usually happen with these kinds of things is the homework is kind of a bear because it's your first time doing it, and they are slightly harder on homework. But for a real exam question, I realize there's 3 integrals already just to run through this problem. It's going to be something a little bit more basic, a fast integration kind of problem. It'll be more about the concept, not about integration by parts in the middle or a trigonometric substitution in the middle. That could be like a 40-minute problem for someone who's well practiced in calculus. We're definitely going to avoid those for sure. And if it comes to it, you'll notice on exam 1, I had partial problems. I had problems where it was like set up the integration by parts table or things like that. This kind of question could be one of those deals. I might say, I'll give you the area, so you're not worried about that on a timed exam. And I might say, calculate just X bar or calculate just Y bar. So these kind of problems could get broken up as well. Because I hear you, this could be, for an even harder function, just a really, really long slog through it. Well, we've got another one to try out. Any other questions or comments first? Yeah, absolutely. Cool, you betcha. Well, let's try out this again a second time. This is one where I feel like, in my opinion, kind of matching what we were saying before, this is one where it'd be a terrible exam question. But as a homework question, it's fair game. We want the exact coordinates of the centroid for region bound by y equals cosine x, y equals 0, and this time we just have a domain on x. So like before, we could plot this by hand, but I want to make Desmos do it because they give us a nice one-to-one scale. I can't plot these very perfectly. If my scale gets a little funky as I draw it out, I'm not going to identify the centroid too well. I could trick myself in thinking I made an answer wrong. So first, let's start with a function. Y is cosine x. There it is. From here, we produce a domain. X less than or equals negative pi over, well, let me try again. Negative pi over 2 less than or equals to x less than or equals to pi over 2. So there's our function right there. Imagine seeing this on exam. I said it would be a terrible problem, but that's because we're doing all the steps on this. However, I wanted to ask the class, what would you say the first coordinate is of the centroid on this?
You know,
Absolutely, this has symmetry working for it, right? If you have symmetry, then you have an automatic guess, first coordinate should be 0 on this thing. In other words, this would bounce right out the y-axis, which has equation x equals 0. It's the second coordinate where I couldn't really guess that. But let's get a good screenshot on this like before and just go from there. Okay, so we've got a function. Imagine this is a real exam question. This is what you're going to be faced with. Then everything else is us adding information as we decide is needed. So first, that's the curve, y equals cosine x, which will be the function f of x as seen in the formulas. Next, well, we also have a lower bound y equals 0, so you might emphasize that by plotting this way, just putting in a bold line. That gives us a bounded region. We want the center of mass. Again, let's try to predict it. We know it's going to lie along this y-axis, but if I go to the middle, should be up or down from there.
You guys want more?
Yeah, I would agree, a little bit downwards. Sorry, what was the other response?
I said 2.4.
About 0.4, yeah, I'd say it's somewhere down there. Reason being is if you cut this in half, what I mean by cutting in half is that that's the coordinate 1, and we put in the coordinate halfway here. There's more mass below this red line or orange line than above. So that means the coordinate should go down. Maybe not by a ton, but I'd say about 0.4 is right in the right neighborhood. So let's run through the steps and give this a try. First, we calculate the area. That is an integral from these bounds, negative pi over 2 to positive pi over 2. We're integrating the function f of x, which is cosine x. But you know what? You can make this integral even simpler. The moment it was observed that we have symmetry on this, you could say you decide to find the area by focusing on that portion right there, and then just double it. In fact, that's a legitimate technique from Calculus 1. Anytime you have symmetry, this is when you have an even function. You can say take 2 times the integral going from 0 to pi over 2. It's not a huge simplification, but I'll take anything I can to make the problem shorter. So we're integrating from 0 to pi over 2 of cosine x. Let's get the antiderivative. Antiderivative of cosine is just sine. Good call. We'll integrate sine from 0 to pi over 2. So this turns into 2 times sine pi over 2 minus sine 0. We have to evaluate the trig functions, but here's a really quick diagram. We have pi over 2 here. We have 0 here. Coordinates on this one are 0, 1. Coordinates on that point are 1, 0. And sine is always the second coordinate. So that tells us sine pi over 2 is exactly 1. Minus sine at 0 is 0. Finally, that tells us the total area under this really, really complicated curve is an integer, 2. That's always kind of amazing in a way. But we got it, folks. We have the total area in the system. Now, we can say here, x bar is clearly equal to 0. That's a legitimate thing to say. If you wrote this on a homework assignment, I will assume that you saw the symmetry and you decided, well, x bar must be 0 based on that symmetry. I would accept that on an exam. If I give you something that involves symmetry and you used it, that's a legitimate thing to do. But we're practicing this problem, so even though it's clearly 0, let's see if we can prove it by really running through the computation. Any questions first before we give this a try? Okay, so let's write out first. We're learning the formula on this thing, so let's just write out down the formula. This helps a lot with getting this in our minds. It's the reciprocal of the area. Integrate from, well, it would be negative pi over 2 to positive pi over 2 to start out. Then it goes x times f of x dx. So let's plug in our information. Reciprocal of area is the reciprocal of 2, so it turns into just a good old 1/2. Now we're integrating from negative pi over 2 to positive pi over 2, x times cosine x dx. Now, when we did the area, we abused symmetry in a nice way to just double a simpler integral from 0 to pi over 2. But if you add a little bit more to that function, x cosine x, you get this situation. That's kind of nice in a way. That would tell me this integral is exactly 0 already, because you have area right here that nullifies each other. In other words, this is an odd function, and the integral of an odd function on a symmetric domain, always 0. But that's almost not fair, because on an exam, I'm only going to give you the one graph. We wouldn't have access to the other graphs. So we probably would compute this out in an exam setting, unless you said that part right there. So it's good practice. We're expecting 0 in a number of different ways. Let's give it a try for real. What would you say the method is on integrating that one right there? Yeah, absolutely. If you're mixing an algebraic with trig, that's our go-to method. So like before, u should be x to make this simple as possible. dv is cosine x dx. Line below, du, I'll just write it as dx, although 1 times dx is fine as well. V, that's just the antiderivative of a cosine x, which we've done once already. We got sine. So using that table here, here's how the problem starts to get going. So think of this now really just practice at this stage. We know the integral should be 0, but let's see if we can land on that. This is going to be 1/2 times uv minus the integral of v du. And let me write that out in a better way. The uv has to be evaluated from negative pi over 2 to positive pi over 2 minus the integral from negative pi over 2 to positive pi over 2 of v du. So all I did here is just set up the formula for integration by parts. Next, it's going to be 1/2. No more stalling on this problem, and start plugging everything in. U times v is x sine x, which is evaluated from negative pi over 2 to positive pi over 2, minus the integral from negative pi over 2 to positive pi over 2 of v times du. So that's going to be sine x dx. So this one's ready to evaluate. We just need an antiderivative here. Any questions to that moment? Yeah.
Can you also get rid of the 1/2 in front by just doing the, where you split in half from where the boundary is 0 power to them?
Let's see. So from 0 to pi over 2, you're meaning, say, on the function x cosine x?
Yeah.
The trouble with that one is it doesn't work with that one because it's an odd function. It would have to look like that right there. You would go from 0 to pi over 2 and just double that area. But the moment you put in an x, we actually can't do the doubling anymore. The way it would go is that just turns into a 0 immediately right at that step. So there's two kinds of integrals along those lines. And for just a quick view on that, because that's a weird calculus 1 topic, let's see if we can pull up the notes on it just to eyeball that a little bit better. I don't remember when I taught that. Fall 2023, it turns out. And the notes that tie all that together should be somewhere over here. This doesn't look like it's on the right track. I have good notes about that somewhere. Maybe it's on this one. Here we go. So these are the things that we're kind of working on when we're looking at those concepts. We have an even function, we're dealing with something like this. And if we want to integrate from, say, -1 to +1, we just double that area. But the one where we go x cosine x looks like this situation right here. So you always get a 0 altogether, as opposed to, I guess I didn't write the integral on that one, as opposed to, let's just write it in right here. Grab the pen tool right quick. So on this one, if we integrate from -1 to +1 of the function x squared is what it was, dx, we can say it's 2 times go from 0 to 1 x squared dx. So that's the nice formula where we're cutting the interval in half in this way and just integrating from 0 to 1. But once we took and put an x there, we've got to this situation, an odd function. And whenever you're dealing with a legitimately odd function, all you do is you put in 0. Kind of weird, but nice in a way. This is one of those weird topics again. There's a bunch of them from Calculus 1 where it doesn't seem like it makes a big deal, but it starts to come up more and more the more you delve into calculus. So for that reason, let's take this whole thing. Let's drop it into our notes in case you want to use it on some of the homework exercises. Those are good tools to be familiar with.
Right.
Yeah,
The bottom one essentially is giving you the same answer, but just one's negative, one's positive.
exactly. Yeah. So they balance to give you a 0, providing you're going symmetrically from -1 to +1 or -2 to +2. Other questions about that or comments? Okay, so on this problem right here, kind of in a weird spot because we're doing this mostly for practice at this moment. We already guessed it should be 0 for the x-coordinate of the centroid. We already checked out that's an odd function in a symmetrical domain. It should be 0. At this stage, we're just doing the grungy numerical computations to really prove our intuition is actually correct. And that's not a bad idea because just because something looks like an odd function is not the proof it's really an odd function. You need to do a little bit of algebra to justify that. So the graphs themselves could be deceiving. So let's keep on running through this. We have 1/2 multiplying. We're putting pi over 2 inside of sine x, but sine at pi over 2 is exactly 1. So that portion just turns into a pi over 2 minus putting in a negative pi over 2. Let's be careful with that one. You would have a negative pi over 2 here. Sine at negative pi over 2 is a -1. So that's just awful. That's a triple negative situation. Then coming over here, we do have a negative sign, but what's the antiderivative of sine x? Any volunteers for that one? Good call. That negative cosine combines with this negative sign. Double negation gives us positive cosine altogether from negative pi over 2 to positive pi over 2. So here's how it's all settling up. We have 1/2 multiplied by pi over 2. That's 3 negatives, so minus pi over 2. And this part's even easier. Cosine at pi over 2 and negative pi over 2, 0 each time. So this is going to turn into +0 minus 0. So we looked at this from 3 different ways. Either way we look at it, we're getting a 0 here. Pi minus pi giving us 0 altogether. So good call, folks. Intuitively, it's 0. It looks like an odd function on a symmetric domain, so it should be 0. But now we know without a shadow of a doubt, it really is. Well, one last coordinate to go, y bar. So that one's not so bad. Let's recall the function is cosine x. And let's write down the formula next. I'll hope for the best that we can fit it on one page. Y bar by formula is the reciprocal of area. We're integrating from negative pi over 2 to positive pi over 2, 1/2 of the function f of x squared. So that's the setup by just putting in the formula. Let me scroll up. The area was 2, so we'll plug in a 2 into that position once again. So 1/2. Next thing I usually do is take out that 1/2. So here it is again. We're going from negative pi over 2 to positive pi over 2 of the function squared. So recall the function is cosine x. So over here, cosine squared x. Well, again, looking at that function, this was a homework problem. You might want to get some intuition on what's going on with it. So let's plot this out. There's cosine. We have symmetry about the y-axis. It's an even function. Cosine power 2 has the same symmetry. Slightly different curve. That means we can shorten up this integral right here. This one is an even function. So up to you if you want to go from negative pi over 2 to positive pi over 2. But let's actually use that symmetry once again. We're going to integrate from 0 to pi over 2.
We wouldn't know this on the graph.
Yeah, that's why this is more like if you're doing it as a homework question, you would have to look at the graphics and make that determination. On an exam, I think most people, me included, I would just use both of those limits. I'll leave it up to you. Should we do it where we use both of the limits? Okay, let's pretend this is a real exam setting, and let's just use the regular limits there. So altogether, this is 1/4. Let's put in a little, well, no, let's put it in like this, from negative pi over 2 to positive pi over 2. I don't want the antiderivative of that function. That's not straightforward at all. U substitution is not even going to help. Anyone recall the method to fix that function? Exactly, good call. The reduction formula goes, here's yet another 1/2. 1 plus cosine 2x. Kind of an amazing formula. So trigonometry enables us to integrate that one pretty rapidly. So my next step, I combine the 4th with a 1/2. So we have an 1/8 now. Here we're finding the antiderivative. There'll be x plus, carefully on this one, starts with a sine of 2x, but that's not the total answer. If you differentiate this, you get 2 cosine 2x because of the chain rule. There's no 2 there. We counteract by putting in a 1/2, and that does the job. Does that make sense to folks on that antiderivative? Awesome. If this was cosine of like 2x squared plus 3, probably you need a u substitution. But if it's a linear function of the variable x, this is always a wonderful method because it saves us lots of writing. We're evaluating from negative pi over 2 to positive pi over 2. So you know what? I think we're going to make it on this one. We should be able to finish off this problem. 1/8 times, first pi over 2 goes in. Pi over 2 plus 1/2. You put pi over 2 here, it's double pi over 2 for sine pi. That's kind of nice because sine at pi is exactly 0. So this is helping us out. Minus, do it all over again at negative pi over 2. So another negative. Kind of hate those double negatives. Plus a 1/2. Putting negative pi over 2 here gives us sine of negative pi, which is the same as sine of pi. Both of these evaluate to 0. Let's put some marks just to convey that. That cancels off. That cancels off. So we have 1/8 of, let's see, pi over 2 plus pi over 2 with the double negatives. That means it's a 1/8 times pi. So it's pi 8. At this stage, we're ready to check our intuition. So the class voted overwhelmingly that this should be below 0.5. 0.4 was a more specific answer. Let's see how close we got. Pi divided by 8, that's like 3 divided by 8. Pi gives us pi, 8. It's a 0.39, so you're off by less than 100ths on that guess. That's pretty remarkable. 0.39 to 2 decimal places. So we did it, folks. We found that the centroid on this one, again, as a homework question, you observe symmetry. That's okay with me. Just say 0 for x bar. We were mostly practicing by computing it out. And, oh, let me reformat my answer. I wanted to convey that x bar, y bar is approximately 0 for x bar, 0.39 for y bar. So we have the center of mass. If you ever say 3D print an object like this, now you know how to balance it under a point. Go to that coordinates right there, approximately. Well, any questions at all, folks, with these kinds of concepts? Okay, as a homework questions, they are long questions. That's one of the things that is like an adjustment phase for Calc 2. Questions get pretty long, and we haven't seen the half of it. Some of them are spectacularly long in chapter 11, but we'll work through them carefully. But if you see a cloud of work like this and you're worried about exams, don't get discouraged. When I write my exams, I also solve them and I time myself, and I imagine I'm doing it as a student. If this was a problem I assigned as an exam question, I would change it up. I might say calculate Y bar exclusively, something like that, to make it reasonable. Well, we're not done with the notes. I'm going to extend the due date on this to make it due after Monday, so October 7th. We have one more question to go, but we'll take our time with this last question. I did change it so that the actual curves line up with the theorem we're about to use. I had curves that did not line up with the theorem before. Well, have a great weekend, folks. If you have any other questions, I'll be happy to help out. Otherwise, I'll see you all in Monday's class.